Hello and welcome to the presentation on data management and automation in the lab of the future. My name is Burkhard Schäfer with BSSN Software, part of Merck, and I'll take you through this topic today. So as you've probably heard and seen, BSSN Software is part of the Merck Group right now. And what we want to talk about today is how we view data as an asset. Because all of those topics of integration and connectivity and Internet of Lab things and data standards and so on, they're a means to an end. They're a means to an end to actually do the data we're producing justice. And data accessibility is really something that is a key enabler because the more accessible we make our data, the more it will be used. So many people are talking about how the lab is turning into one of the most relevant data producers in an organization. But something that we're not hearing too much about is how we need to think about not only the technology side of things, but also the process side of things. Because data accessibility not only means that we need data, it also means that we need to set up our business processes in a way that that data can really be harvested. And just like with any business process, things that happen in the lab need to be reviewed the same way. So in a traditional business process, what you typically see is everything happens for a reason, right? For a typical business process, there is a certain trigger or a trigger question that stands behind a scientific experiment. Now, this trigger question is what kicks off the process. And then what we typically do is we heavily optimize the process execution itself. So we get decent latency, that we achieve a high level of throughput. And that is what we organize everything around, this topic of efficiency in getting stuff done. However, as we do that, certain things fall behind. We only capture those parts of the outcome that answer that very trigger question that launched the experiment. And supporting data is either dropped or lost in silos. Now, obviously, we're delivering the business outcome here, but this is not very sustainable from a data perspective. Now, a data-enabled business process works a bit differently. It doesn't work very differently in terms of what people do, right? Because the tasks are still the same, but it's different about how it thinks about the data. So in a data-enabled business process, the first thing we do is we admit that we don't know all the questions yet, that we will be able to answer based on the data we're generating. However, we have the expectation that we can learn from what we are doing, either by looking at individual experiments again later, or by reviewing them in aggregate, looking at trends, looking at patterns. And to facilitate that, we need to think different about the data capture during the process execution. We want to capture as much raw data and data as we can during the process or experiment execution. And we want to annotate that raw data with sufficient metadata context so we can find it again later. And that allows us to access the data again at a later point in time. And we may be able to aggregate the data as well. And we do that enough so we can trace things back. And we use open and standard data formats in order to ensure the interoperability. And that will then allow us the reuse of the data. And you may know these concepts under the term of the FAIR principle. So we're not really changing a lot about what the people in the labs are doing, but we are basically setting up a big vacuum cleaner next to what is being done to make sure that all the data that is being generated are being absorbed and are being put into context so that we can then deliver that data to any stakeholder that has a need. So how can I achieve that integration? Well, we have two aspects in this. First of all, we need communication to get systems to talk to each other. And we need to represent data because that's what we are generating and that's what's parameterizing the experiments that are happening. So if we look at communication standards, those sound like a good thing, right? However, if all we do is have a common communication protocol, that leaves us with proprietary data structures. As soon as we've acquired the data using that open protocol, well, we need to put it somewhere, and that's yet another silo. So a communication protocol is nice, but not enough. An open and interoperable standard file format is also interesting. However, a file format alone is not suitable for systems where components need to communicate, because at least according to my book, copying files and moving them around is not communication. But if we combine the two, an open communication protocol and a standardized file format that is able to describe the data that I'm handling in the lab, I have what I need for end-to-end integration. And that's what this is about. So saying that data and communication need each other means two things. It means I need a communication standard and I need a data standard. And for communication, the most appropriate one for the lab environment is the CELA initiative. And you'll be hearing more about that in this presentation. And on the data standard side, we see Animal as the most promising contender to actually deal with the data that's being produced. So let's take a look at these. CELA 2 is the new version of the CELA standard family, and it's intended to sort out communication in the lab of the future. And I think that they've done a pretty good job with that. So as I said, CELA is a communication protocol. It's not a data format. It's a means of communicating. It's based on modern web technologies such as HTTP2 and gRPC. And it uses a feature mechanism to standardize commands for common capabilities of instruments. Now, CELA said we don't want to reinvent the wheel and build yet another data format. So they've partnered with the Animal Initiative for the data. And CELA has over 2,000 members, and it's primarily active in Europe and North America. And if you're interested, we've got the link to their website right here. Now, Animal, looking at it from the data format perspective, complements the communication protocol provided by CELA quite nicely. You can think about CELA providing the envelope for sending messages around, and Animal being one of the possible payloads that you can put into that envelope to actually send analytical and biological data in an open XML format. Animal also works standalone, so you can just store XML files on your hard disk that contain analytical and biological data. Animal comes out of ASTM and can handle both analytical chemistry, but also biologics data, making it the most versatile data standard to my knowledge that has a really decent coverage of measurement and process techniques. It supports data from multiple techniques. So you can use one data format for many different types of experiments, which is quite powerful and gets us decent reuse of our tools. And we can even combine different techniques in one experiment, in one data format, and visualized using the same tool, which is another very powerful capability. Animal captures sample and process data as well, not only the results. So we have traceability of how an instrument was configured, who was the operator, and what software was used, so that we have reproducibility. And for the regulated communities, there are features such as audit trails, digital signatures, and validation capability, which are quite interesting. Now you will find that many things in Animal are really focusing around data accessibility and ease of adoption, because a data standard needs to be at least as cost effective as a proprietary alternative. So obviously that is why we want those standards. And the fact that Animal is based on the XML ecosystem means that the data that is stored in Animal can be used out of the box in tens of thousands of tools today, even if they were not specifically built for the lab. And so many of the design choices in Animal really led to a low total cost of ownership, which is something that we, as both a vendor and an end user, are really looking for. So where are we today in terms of tooling and coverage of what can be done in this standardized and interoperable lab of the future? Well, here is a little model that allows us to look at this. So the first, excuse me, the first order of business is data aggregation. So can we bring all of our analytical and biological data into one common format? Yes, we can. And Animal is the format that we use for that. And Sila is paving the last mile to the instrument so we can control the instrument to tell it what to do. And we have over 200 instrument models available right now for which there are converters and adapters. Now, once I have that data in one common format, one thing that is low-hanging fruit is to then build visualization technology on top of that, which means I can use a single tool for all my measurement techniques across platforms and across devices. And here we've implemented solutions on Windows, on Mac OS, a browser-based experience, as well as mobile apps. So I can really get to the data that I want to work with on any device that matters to me. Next is domain-specific processing, where I can do processing decoupled from vendor software so that I can complement the features in the instrument software with additional analytics and processing capabilities. And for that, we have a pluggable data action framework that can sit on top of the standardized information set, where we offer quite a few already out of the box, and more can be plugged in using open interfaces. All of those workflows need to be orchestrated so that the user can be supported through data acquisition and execution. And that's where many standards can play together. Sila for the communication, Animal for handling the data, and BPMN to describe the workflow. And all of that data then needs a home, which is a cloud-based data lake, where we also have the capability to extract arbitrary values, where we have a solid metadata strategy, where we combine the Animal format plus a scalable NoSQL architecture to ensure that that data can be represented and navigated and searched efficiently. Now, if I combine those 5 pillars, I can play the data intelligence endgame. I can feed those pieces of data into my machine learning and AI initiatives. I can build data mining on top of it. I can run statistics and visualization. So quite holistic approach. And here are a couple of examples of what that can look like. So here we've got an HPLC data set that's coming from Thermochromeleon, where we have a nice converter. And you can now look at that data within your web browser, and this is fully interactive. Now, same data format, different measurement technique, where you can put a Perkin-Elmer UV WinLab spectroscopy experiment into Animal. That's what that looks like in your web browser. And you can go on. Different types of measurement techniques, for example, plate-based assays, quite popular, where in this case we have an Envision plate reader, and that same data format, Animal, and the same software can handle the data from that technique as well. We can go on to Raman spectroscopy, where the data in this case comes from Analyze IQ, 5 spectra in one Animal file. And if we're looking more into the biologic space, here is an experiment where we're doing antibody purification with process chromatography, where we have a number of sensors attached, and each of those come across as a spark line, and then you can go and pick the ones that you want to see. And this is GE ECTA unicorn data. If you're looking for mass spec, that's obviously also supported here. You've got your chromatograms and you've got your spectra, and you can drill down from your chromatograms to pull out the spectra underneath. And of course, everything here is fully interactive. Those are not just images. You can also move over to the desktop. So in this case, we are using an NMR data set in Animal format. And it comes from Brooker Topspin. And by now, I think we're seeing the pattern, how powerful this is to be able to represent all of those different types of instruments in the same data format and to be able to use one consistent set of tools with that. Here, again, a biologics example where we're using Sartorius MFCS Win and a Roche ZX Hi-Res cell analyzer together, and we are creating this beautiful overlay with just a couple of clicks, which usually would be hours of Excel kung fu. So this was the data side. Let's actually put the connectivity into the mix. And that allows us to then build sophisticated integration approaches. And so let's say we have a LIMS somewhere in our lab of the future, and the LIMS should be configured to talk to the different instruments. Now comes the SEALA approach. The SEALA approach allows us to perform discovery, so we can recognize the different services or devices that are available in the lab. So in this case, we would be recognizing a balance and maybe a chromatography data system, and those services respond and are inventoried by the LIMS. Now, next up, these instruments and services can describe their capabilities, and the LIMS learns how to communicate with those services and what the data structures look like. And the different commands that are supported by such a service are described using SEALA feature definitions. And the data that is being returned after an experiment is described using animal technique definitions. That way you can build mappings and configure workflows quite easily on the LIMS side to define what the commands are you want to send to an instrument and what you want to do with the data that's coming back. And that allows us to perform instrument control to submit samples using SEALA 2, and we get back a complete and traceable animal data package that describes what the respective service did. And then the LIMS can go and either just extract the data that it wants, or then populate a data lake with this and move on. So quite powerful. Now, obviously, each type of instrument or service would have different capabilities. So a chromatography data system would allow me to submit batches, to review the status, get the audit trail, and obviously the analytical data that comes back would also have a different structure. But to the LIMS, that doesn't matter. The LIMS can discover automatically what that data looks like and what the commands are that can be used to talk to that service. So one of the big questions is, where is the adoption? How can we enable a standards-based open ecosystem that actually lets us do all this? And for that, the first thing we need to look at is, well, these standards look like a great idea, but what is their value and what is the total cost of ownership of a given standard? Because any standard needs business justification, like any other investment, and it must provide greater value than alternative proprietary approaches. So we can quantify that. We can look at how hard it is to create such a standardized file, or how hard it is to read the information that is inside it, or how to store and manage that file. Can we encode real-world lab experiments in it, the types of experiments that we are doing? How hard is it to consume only parts of a file, or to verify the correctness of a file, or to even verify the integrity of a file? And a good thing to do is, let's look at the utility of a data standard by imagining that we have a file in a given standard format. Now you imagine having that file in your hand or on your disk. Now, what can a user actually do with that? If it's an XML file, okay, lots of XML tools. But if it's a format that actually requires specific libraries that is hard to get to and so on, obviously the utility of such a format would be limited. And these are the questions we need to ask. And that way we can figure out what the value and the total cost of ownership of a standard is for our given use case, right? There is no silver bullet. It's always depending on what we want to do to pick the right tool for the job. And as you know, Animal leverages XML, so it's part of that XML ecosystems. This means that tools and libraries are readily available in all relevant languages, and it's readable even by non-lab tools, which means that we don't need specific tooling written for our workflows. We can piggyback on a huge industry of the Microsofts and the IBMs and the Red Hats of the world that can directly consume data out of XML. And I can take an animal file, throw it into Crystal reports, and get a decent report out of it, even though the people who wrote Crystal reports probably may not have known what a lab even is. And this quick start is really powerful. Most developers already know XML, and the long-term readability obviously makes it an ideal choice for archival scenarios. So we're quite proud that that we're not the only ones who think that this is a good idea. So Frost & Sullivan presented an innovation award in 2019 to BSSN software in the Global Analytical Instrumentation Informatics category. So that's basically your instrument software category, where Frost & Sullivan thought that BSSN software was the most innovative player in that space. And we're proud to announce that we have received the same award again in 2020. So twice in a row. And we're quite proud of that. So to summarize, I think we can say, yes, we can. And given the upcoming elections or the current elections, we can. And what can we do? We can deliver on the promise of standards and interoperability today. We can reduce the complexity of instrument interfaces and capture the value of a connected lab ecosystem using things that are common sense and that are available off the shelf with minimal effort. So with that, thanks so much for your interest, and I'd like to close the session. And please feel free to reach out with any questions. Thank you.